Hello everyone and welcome to Audio White Papers. In this episode, I will be reading part 2 of 4 of Ethereum. If you like what we are doing here, please subscribe to the channel and like the video. We intend to do an audio collection of cryptocurrency white papers that have a significant amount of community support, as well as some that pique our personal interest. If you have any interest in supporting the project, in the description of the YouTube video and the podcast, there is a link to donate Bitcoin and Ethereum to the channel. Also note that aside from this introduction, the information that I am reading is not my own, and I will read as written by the original author, who is not me. If you have any questions, concerns, or requests for future audio white papers, please request them in the comments below or email audiowhitepapers@gmail.com. Thank you for watching and thank you for listening. Ethereum. The intent of Ethereum is to create an alternative protocol for building decentralized applications, providing a different set of trade-offs that we believe will be very useful for a large class of decentralized applications, with particular emphasis on situations where rapid development time, security for small and rarely used applications, and the ability of different applications to very efficiently interact are important. Ethereum does this by building what is essentially the ultimate abstract foundational layer, a blockchain with a built-in Turing-complete programming language, allowing anyone to write smart contracts and decentralized applications where they can create their own arbitrary rules for ownership, transaction formats, and state transition functions. A bare bones version of Namecoin can be written in 2 lines of code, and other protocols like currencies and reputation systems can be built in under 20. Smart contracts, cryptographic boxes that contain value and only unlock it if certain conditions are met, can also be built on top of the platform with vastly more power than offered by Bitcoin scripting because of the added values of Turing completeness, value awareness, blockchain awareness, and state. Ethereum Accounts. In Ethereum, the state is made up of objects called accounts, with each account having a 20-byte address and state transitions being direct transfers of value and information between accounts. An Ethereum account contains 4 fields: a nonce, a counter used to make sure each transaction can only be processed once, the account's current ether balance, the account's contract code, if present, the account's storage, empty by default. Ether is the main internal crypto fuel of Ethereum and is used to pay transaction fees. In general, there are 2 types of accounts: externally owned accounts controlled by private keys, and contract accounts controlled by their contract code, a transaction. In a contract account, every time the contract account receives a message, its code activates, allowing it to read and write to internal storage and send other messages or create contracts in turn. Rather, they are more like autonomous agents that live inside of the Ethereum execution environment, always executing a specific piece of code when poked by a message or transaction, and having direct control over their own ether balance and their own key/value store to keep track of persistent variables. Messages and transactions. The term transaction is used in Ethereum to refer to the signed data package that stores a message to be sent from an externally owned account. Transactions contain the recipient of the message, a signature identifying the sender, the amount of ether to transfer from the sender to the recipient, an optional data field, a start gas value representing the maximum number of computational steps the transaction execution is allowed to take, a gas price value representing the fee the sender pays per computational step. The first three are standard fields expected in any cryptocurrency. The data field has no function by default, but the virtual machine has an opcode using which a contract can access the data. As an example use case, if a contract is functioning as an on-blockchain domain registration service, then it may wish to interpret the data being passed to it as containing two fields, the first field being a domain to register and the second field being the IP address to register it to. The contract would read these values from the message data and appropriately place them in storage. The start gas and gas price fields are crucial for Ethereum's anti-denial of service model. In order to prevent accidental or hostile infinite loops or other computational wastage in code, each transaction is required to set a limit to how many computational steps of code execution it can use. The fundamental unit of computation is gas. Usually a computational step costs 1 gas, but some operations cost higher amounts of gas because they are more computationally expensive or increase the amount of data that must be stored as part of the state. The intent of the fee system is to require an attacker to pay proportionally for every resource that they consume, including computation bandwidth and storage. Hence, any transaction that leads to the network consuming a greater amount of any of these resources must have a gas fee roughly proportional to the increment. Messages. Contracts have the ability to send messages to other contracts. Messages are virtual objects that are never serialized and exist only in the Ethereum execution environment. A message contains the sender of the message, implicit, the recipient of the message. Essentially, a message is like a transaction, except it is produced by a contract and not an external actor. A message is produced when a contract currently executing code executes the call opcode, which produces and executes a message. Like a transaction, a message leads to the recipient account running its code. Thus, contracts can have relationships with other contracts in exactly the same way that external actors can. Note that the gas allowance assigned by a transaction or contract applies to the total gas consumed by that transaction and all sub-executions. For example, if an external actor A sends a transaction to B with 1,000 gas, and B consumes 600 gas before sending a message to C, and the internal execution of C consumes 300 gas before returning, then B can spend another 100 gas before running out of gas. Ethereum State Transition Function. The Ethereum State Transition Function, apply bracket S, TX, close bracket, right arrow S, can be defined as follows. 1. Check if the transaction is well formed, the signature is valid, and the nonce matches the nonce in the sender's account. If not, return an error. 2. Calculate the transaction fee as start gas times gas price and determine the sending address from the signature. Subtract the fee from the sender's account balance and increment the sender's nonce. If there is not enough balance to spend, return an error. 3. Initialize gas equals start gas and take off a certain quantity of gas per byte to pay for the bytes in the transaction. 4. Transfer the transaction value from the sender's account to the receiving account. If the receiving account does not yet exist, create it. If the receiving account is a contract, run the contract's code either to completion or until the execution runs out of gas. 5. If the value transfer failed because the sender did not have enough money, or the code execution ran out of gas, revert all state changes except the payment of the fees and add the fees to the miner's account. 6. Otherwise, refund the fees for all remaining gas to the sender and send the fees paid for gas consumed to the miner. For example, suppose that the contract code is, there are a couple lines of code here. If you'd like to reference it, check the Ethereum State Transition Function section of the white paper. Note that in reality, the contract code is written in the low-level EVM code. This example is written in Serpent, one of our high-level languages, for clarity and can be compiled down to EVM code. Suppose that the contract's storage starts off empty and a transaction is sent with 10 Ether value, 2000 gas, and 0.001 Ether gas price, and 64 bytes of data, with bytes 0 to 31 representing the number 2, and bytes 32 to 63 representing the string Charlie. The process for the state transition function in this case is as follows. 1. Check that the transaction is valid and well formed. 2. Check that the transaction sender has at least 2000 times 0.001 equals 2 Ether. If it is, then subtract 2 Ether from the sender's account. 3. Initialize gas equals 2000. Assuming the transaction is 170 bytes long and the byte fee is 5, subtract 850 so that there is 1,150 gas left. 4. Subtract 10 Ether from the sender's account and add it to the contract's account. 5. Run the code. In this case, this is simple. It checks if the contract storage at index 2 is used, notices that it is not, and so it sets the storage index 2 to the value Charlie. Suppose this takes 187 gas, so the remaining amount of gas is 1,150 minus 187 equals 963. Add 963 times 0.001 equals 0.963 Ether back to the sender's account and return the resulting state. If there was no contract at the receiving end of the transaction, then the total transaction fee would simply be equal to the provided gas price multiplied by the length of the transaction in bytes, and the data sent alongside the transaction would be irrelevant. Note that messages work equivalently to transactions in terms of reverts. If a message execution runs out of gas, then that message's execution and all other executions triggered by that execution revert, but parent executions do not need to revert. This means that it is safe for a contract to call another contract as if A calls B with G gas, then A's execution is guaranteed to lose at most G gas. Finally, note that there is an opcode create that creates a contract. Its execution mechanics are generally similar to call, with the exception that the output of the execution determines the code of a newly created contract. Code execution. The code in Ethereum contracts is written in a low-level stack-based bytecode language referred to as Ethereum Virtual Machine Code, or EVM code. The code consists of a series of bytes where each byte represents an operation. In general, code execution is an infinite loop that consists of repeatedly carrying out the operation at the current program counter, which begins at 0, and then incrementing the program counter by 1 until the end of the code is reached, or an error or stop or return instruction is detected. The operations have access to 3 types of space in which to store data: the stack, a last in first out container to which values can be pushed and popped; memory, an infinitely expandable byte array; the contract's long-term storage, a key value store. Unlike stack and memory, which reset after computation ends, storage persists for the long term. The code can also access the value, sender, and data of the incoming messages, as well as block header data, and the code can also return a byte array of data as an output. The formal execution model of EVM code is surprisingly simple. While the Ethereum virtual machine is running, its full computational state can be delivered by the tuple block state, transaction, message, code, memory, stack, PC, gas, where block state is the global state containing all accounts and includes balances and storage. At the start of every round of execution, the current instruction is found by taking the pcth byte of code, or 0 if pc greater than equals len bracket code, close bracket, and each instruction has its own definition in terms of how it affects the tuple. For example, add pops 2 items off the stack and pushes their sum, reduces gas by 1 and increments PC by 1, and store pops the top 2 items off the stack and inserts the second item into the contract storage at the index specified by the first item. Although there are many ways to optimize Ethereum virtual machine execution via just-in-time compilation, a basic implementation of Ethereum can be done in a few hundred lines of code. Blockchain and mining. The Ethereum blockchain is in many ways similar to the Bitcoin blockchain, although it does have some differences. The main difference between Ethereum and Bitcoin with regards to the blockchain architecture is that, unlike Bitcoin, Ethereum blocks contain a copy of both the transaction list and the most recent state. Aside from that, 2 other values, the block number and the difficulty, are also stored in the block. The basic block validation algorithm in Ethereum is as follows. 1. Check if the previous block referenced exists and is valid. 2. Check that the timestamp of the block is greater than that of the referenced previous block and less than 15 minutes into the future. 3. Check that the block number, difficulty, transaction root, uncle root, and gas limit bracket various low-level Ethereum specific concepts are valid. Various low-level Ethereum specific concepts are valid. 4. Check that the proof of work on the block is valid. 5. Let S square bracket 0 be the state at the end of the previous block. 6. Let TX be the block transaction list with N transactions. If any application returns an error, or if the total gas consumed in the block up until this point exceeds the gas limit, return an error. 7. Let S_final be S*(n), but adding the block reward paid to the miner. 8. Check if the Merkle tree root state of S_final is equal to the state root provided in the block header. If it is, the block header is valid, otherwise it is not valid. The approach may seem highly inefficient at first glance because it needs to store the entire state with each block, but in reality, efficiency should be comparable to that of Bitcoin. The reason is that the state is stored in the tree structure, and after every block, only a small part of the tree needs to be changed. Thus, in general, between two adjacent blocks, the vast majority of the tree should be the same, and therefore the data can be stored once and referenced twice using pointers, i.e., hashes of subtrees. A special kind of tree, known as a Patricia tree, is used to accomplish this, including a modification to the Merkle tree concept that allows for nodes to be inserted and deleted and not just changed efficiently. Additionally, because all of the state information is part of the last block, there is no need to store the entire blockchain history. A strategy which, if it could be applied to Bitcoin, can be calculated to provide 5 to 20 times savings in space. A commonly asked question is where contract code is executed in terms of physical hardware. This has a simple answer. The process of executing contract code is part of the definition of the state transition function, which is part of the block validation algorithm. So if a transaction is added into the block, B, the code execution spawned by that transaction will be executed by all nodes now and in the future that download and validate block B. That's it for this episode of Audio White Papers. Again, if you like our channel, please subscribe, please like the video, and there's a donation link below. Thank you for watching, and thank you for listening.